Morning. First, any questions or concerns? So I want to get through, if possible, I want to finish chapter 12. I don't think I'm going to be able to do it. I don't think we're going to be able to do it, but I want to finish the majority of it. So chapter, we stopped about right here. So conduction speed in axons. Remember that in the central nervous system, axons are called nerve fibers. In the peripheral nervous system, they're called, sorry, I'm changing it. In the central nervous system, they're called tracts. In the peripheral nervous system, they're called fibers. So depending on two factors is the conduction speed. The diameter of the nerve fiber occurs along the surface of a fiber. So with increased surface area comes increased speed. In small unmyelinated nerve fibers, the nerve fibers, so I'm sorry, let me say this again. So two factors, diameter of the nerve fiber. Were we right here before? Is this where we were? Did we talk about an action potential before?
I think so.
So we were farther along than this.
We were definitely, we did unmyelinated versus myelinated. Yeah, we did that.
We did this. Why I wonder, I thought this was really, we were really, I thought we were more ahead than this. Let me look really quick. You guys remember where we were at?
Hey, excuse me. Caitlin is trying to get in. She's on an airplane and she just
I can try to get her in. I don't, let me try something really quick. Stop sharing. Let me try to, I don't really know how to invite her, but I can try.
I think she said she's trying to get it. I don't know if she's trying to get in.
I can't spend a lot of time doing this because we have gotten behind. Let me see. How did I do it before? me try. What else can I try? Um, um, you know what? Let me try doing something really quick, see if this works.
She said she may be having trouble on her end, so maybe we should just move on.
Well, let me do one thing because I just thought of something.
Okay, thank you.
Email, copy invite link. Now, I have to remember what her email is. Can you text her and ask her what specifically her email is?
Yes.
For hack. Or whatever email she can use where she's at right now.
Okay, it's Caitlin.
All right, give me 1 second. I'm sorry, 1 second. K I
KAITLYNEBERTS
or EBERTS
2011
2011.
011
Say it one more time.
2011
Okay. At what's the rest of it? You know what the rest of it is?
Yeah, at gmail.com.
Okay, so Caitlin Eberts 2011 at gmail.com. Okay. I'm gonna class. Let's see if she can do it this way. Okay, tell her I just sent her an email, the email link for it. See if she can get in that way. But I need to get started here.
Will do. Will do. I understand.
No, I appreciate you being the mediator there. Where were we? So did we go through, I'm sorry, I'm even asking this question, but did we go through gated channels? Did we go through action potentials and local potentials? I'm going to move up because I thought we were farther ahead than this also, but I can't remember exactly where we stopped. Normally I make a note of it, but I think my notes are off. Bear with me. I know where to look because I don't want to skip ahead, but I don't know where we left off. And I really hate watching myself, but we're going to watch him for 1 second. Figure out where we were. Maybe. Okay, we were right there. Oh, no, I don't want to do that, but I just did it anyway. Stop. No, stop, stop. Stop, 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 stop. Okay, close that out. Leo, you're not helping, bud. Leo, no way. Sorry, my cat decided he was going to jump on my keyboard. No.
Are you looking to see where our
I know
bookmark
where
is?
we're at now.
Okay.
Because I just looked at the very end of that recording, so I have a good idea of where we are right now. Okay, so we were about right here. She's gonna go over again. So graded potentials are graded, meaning that they vary in magnitude according to the strength of the stimulus. They're decremental and can undergo summation. So they get weaker as they spread away from the point of origin, but they can sum with other potentials. They're reversible. Once a stimulus ceases, the cation diffusion quickly returns to the regular resting membrane potential. So once they, then the membrane potential gets disrupted, once the stimulus that disrupted it stops, the resting membrane potential quickly returns back to normal. They're also excitatory or inhibitory, meaning that they can hyperpolarize or depolarize the cell's membrane. The greater the stimulus strength, the larger the amplitude of the graded potential. So the larger the stimulus, the greater the amplitude. The more intense or prolonged the stimulus is, the more gated channels will open for a longer period. The result is more sodium can enter the cell and voltage changes will occur more than it would with a weaker stimulus. This relationship between stimulus strength and amplitude also exists for a hyperpolarized graded potential. So remember what it means to be depolarized or hyperpolarized. Depolarized meaning the membrane becomes less polar. Do you think what it means to decline in health means that you become less healthy? So if the membrane is always polar, if you become depolarized, it becomes less polar. If it gets hyperpolarized, it becomes even more polar. So depolarization, meaning there's a less of a separation in charge. Hyperpolar. Okay. Hyperpolarization, meaning the membrane potential becomes more polar. So a large stimulus is going to open more ligand-gated channels and more ions are going to flow across the plasma membrane. There is a voltage variable. So different stimuli can have different amplitudes that can summate or cancel each other out. The net result is a larger or smaller graded potential. Nevertheless, these are decremental. So they will start to die out within a few millimeters of their point of origin. Therefore, graded potentials are only useful for short distances. Paisley, Pacers, come here. If depolarizing potentials summate, the net result is a larger depolarizing graded potential. So if you get multiple depolarizing graded potentials, they summate to result in a larger depolarizing graded potential. A depolarizing graded potential and a hyperpolarizing graded potential can cancel each other out. If one makes it more positive, one makes it more negative. One makes it more positive and one makes it more negative. They're going to neutralize one another. So a depolarizing graded potential is a stimulus that causes a reduction in the difference in charge across a membrane, making the inside of the cell less negatively charged. A hyperpolarizing graded potential is going to cause the cell to become more negatively charged. There's a balance between these two types of potentials. This is really important when we start talking about neuronal integration, where the neuron can process many different inputs. And it does it through the adding of these different graded potentials. For example, acetylcholine is a neurotransmitter that usually causes depolarization of a neuron, with more sodium entering into the cell. Therefore, the inside of the cell becomes more positive, resulting in the chances of a cell being more likely to reach a threshold and fire an action potential. Glycine, on the other hand, causes the cell to become hyperpolarized, where the cell membrane becomes more negative than it was before. So it's less likely to reach a threshold and fire an action potential. Graded potentials occur as a result of the opening of mechanical or gated channels. Whether a membrane potential becomes more positive or negative depends on the type of channel that opens. It depends on what flows through that channel. If we introduce more positive charges into the cell, it's going to become less negative because it's already negative. So you add more positive to it and it becomes less negative. If you add more negative to it, it becomes more negative. If you take positive ions like potassium out of the cell, you're going to make the inside of the cell more negative. Oh, no, wait, I'm sorry. Let me say that differently. Oh, no, that's right. If you take more positive ions out of the cell, you're going to make it more negative. Which type of potential does not decay with distance? And we haven't answered this question, so I'm just going to give you the answer. Action potentials don't decay with distance. What does it mean to decay with distance? Do you remember that term from a few minutes ago? What that means is that it's decremental. So action potentials are not going to be decremental. They don't decay with distance. Action potentials result in a dramatic change. So this is in contrast to local potentials. Action potentials result in a dramatic change produced by voltage-gated ion channels in the plasma membrane. These will only occur, action potentials will only occur when there is enough of a density of voltage-gated channels. So most of the cell soma, remember that's a cell body, most of the cell soma only has 75 channels per micrometer squared. The trigger zone contains 350 to 500 channels per micrometer squared. So if an excitatory local potential arrives at the trigger zone, it can open up the channels and generate an action potential. An action potential is a rapid up and down shift in the membrane's potential. Very quick. And it's only going to happen at the trigger zone because there has to be enough channels for it to occur. So let's go through what an action potential is. So when a steadily rising local potential arrives at as a local current at the axon hillock, remember this is that hillock, here's the trigger zone. So when a steadily arising local potential arrives at the axon hillock, it depolarizes the membrane. Remember what depolarization means? That means that the membrane, the inside of the cell is becoming more positive. It's normally at a -70. So it's slowly moving up towards a more negative, a less negative value. If the local potential rises to a critical depolarization voltage, the threshold, which is -55, slowly becomes less negative. If it reaches this -55, it will open voltage-gated channels. And it's going to do it very, very quickly. So if it reaches that threshold, if we get enough depolarization where we reach the threshold, voltage-gated channels are going to open at that -55 millivolts. And the neuron is going to produce an action potential with voltage-gated sodium channels opening quickly, while voltage-gated potassium channels start to slowly open. So at this point, when we reach this threshold, we have sodium channels that are quickly opening, while potassium channels are only starting to open. A few sodium channels open, but as more sodium enters the cell, it further depolarizes the cell. So this is a positive feedback loop. A few channels open. Remember, sodium is much higher concentrated outside of the cell. So if sodium channels open, sodium is going to rush into the cell. Sodium is positively charged. So it's going to make the inside of the cell more positive. And when these sodium channels open at a negative 55, if some sodium starts entering the cell, more and more of the membrane is going to reach that threshold of negative 55. If they all start at negative 70. So the result is that more as the sodium channels start to open, more of the cell is going to get depolarized, causing more channels to open. Because more of the membrane is going to reach that negative 55. This is a positive feedback loop where the change in the first change in voltage is going to cause more change in voltage, which is going to result in more channels opening. The first channels open, they cause more channels to open. As the potential rises past 0 millivolts and peaks at, it's going to peak at positive 35 millivolts. So now we've gone from the inside of the cell being a negative 70 to negative 55, and now it's a positive 35. And so at this point, the polarity is reversed. The inside of the cell is more positive than the outside. At this voltage, the sodium channels get inactivated. So sodium stops flowing into the cell. It slowly stops flowing. At this point, the potassium channels that started opening at the very beginning at threshold, but they don't open as fast as the sodium channels, they become fully open. And finally, you know, they started to open here, but they open a lot slower than sodium channels do. So at this point, they're fully open, and the sodium channels are starting to close. So potassium then moves out into the extracellular fluid, causing the inside of the cell to become more negative. Until the voltage reaches the threshold and returns to the resting membrane potential. The potassium channels are going to stay open longer than the sodium channels, so slightly more potassium leaves than sodium enters. They take longer to open, and they're slower to close. The result is that we get a hyperpolarization of the membrane, where the inside of the cell is more negative. Bear with me, guys, just for a moment. Mom, can you come and see if you can take her out? I've got a dog on my lap who's not been feeling very well. She had some moments during the night, and I can just hear her intestinal tract working away. And I think she probably needs to go out. Thank you, Mom.
When did you have her out last?
I actually had her out at during my break, so about right before then. Yeah, I can hear her intestinal tract moving, so I think she needs to go out. So what's occurring here, starting at the very beginning, this gradual potential is adding up, and we're getting some negative, some positive. If the membrane becomes negative enough that it reaches this threshold, or excuse me, it becomes positive enough. So we start at -70. If the membrane continues to depolarize until it reaches this threshold of -55, it's going to open a bunch of sodium gates. These are voltage gated sodium channels. At the same time, we're going to get some potassium channels that are not going to open as fast, but they start to open. And at that point, we get this rapid depolarization because sodium is rushing into the cell. And as more sodium enters, it's going to cause more sodium channels to open until the polarity is reversed at +35. At that +35, the sodium channels are now going to close. And the potassium channels that started to open here are now completely open. And this potassium channels when they open, they're going to release potassium out of the cell, causing the inside of the cell to become more negative again. Until we get to the bottom where the channels will start to close again, these potassium channels. And the potassium channels, they're slower to open and they're slower to close. That's what causes the hyperpolarization, is this potassium. So depolarization is caused by the sodium. Repolarization is caused by the potassium. Questions? Give her back to me then. Oh. Okay. So during an action potential, the sodium and potassium are going to switch places across the membrane. During the hyperpolarization, because the sodium gradually diffuses into the cell, the membrane voltage is going to return to the resting membrane potential. So at the resting membrane potential, both the sodium and potassium channels are closed. During the depolarization, the sodium channels are open, sodium is entering the cell, and the potassium channels are beginning to open. At the +35 millivolts, meaning the peak of the action potential, the sodium channels close and the potassium channels are now fully open, and the potassium leaves the cell. Depolarization ends and repolarization begins. Paisley, stop. The sodium channels close and potassium is closed at the end of repolarization. So depolarization, sodium channels are open. Repolarization, potassium channels are opening and the sodium channels are closing. When repolarization is complete, the sodium channels are closed and the potassium channels are closing. Then the cell will hyperpolarize until the potassium channels are completely closed. So at threshold, the sodium channels are opening and the potassium channels are slowly opening. Depolarization, the sodium channels are opening very fast. The potassium channels are opening, but not as fast. At repolarization, the sodium channels are closing quickly and the potassium channels are fully open. During hyperpolarization, the sodium channels are closed and the potassium channels are getting ready to close. They're slowly closing. Do you have questions for me? So action potentials follow this all or none law. If a stimulus depolarizes the membrane enough to reach threshold, an action potential is fired at its maximum voltage. However, if the deep threshold is not reached, no action potential will be generated. So this is an all or nothing, either it happens or it doesn't. And that it always goes to completion. A greater local potential will not result in an increased amplitude of an action potential. It always goes to the same intensity every time. It's also non-decremental, meaning it doesn't get weaker with distance. An action potential at the end of an axon is not going to be weaker than one at the trigger zone. It's also irreversible. Once it occurs, it goes to completion every time. One thing that we have to also keep in mind, because currents are going to flow in one direction, well, what keeps them flowing in one direction? During an action potential and a few seconds afterwards, it's difficult or impossible to stimulate the region of the neuron to initiate another action potential. This is because once the sodium gates open, they cannot be reopened until they're completely closed. So during the initial, this absolute refractory period, until the sodium channels are completely closed, all of them are closed, they can't be reopened. During the relative refractory period, a new action potential may be triggered, but only by an exceptionally strong stimulus because we're at a hyperpolarization. Remember, that means that the cell is more negative than it is at the resting membrane potential. So it's going to be harder for a stimulus to reach threshold. So a really, really strong stimulus will initiate an action potential, but a weaker one will not. So this relative refractory period is going to last until the hyperpolarization ends. So absolute is the gate, the sodium gates cannot be reopened until they're all closed. The relative refractory period is caused by the hyperpolarization. Keep this in mind for a few minutes from now because this is going to be important. So local versus action potentials. Local potentials are produced by gated channels on the dendrites or the soma. Remember, the soma is a cell body. Action potentials are produced by voltage gated channels on the trigger zone. Local potentials may be a positive or a negative voltage change. Action potentials are always depolarizing, they're always negative. Sorry, they're always positive. It's always a positive voltage change. Local potentials are graded, meaning they're proportional to the stimulus strength. Action potentials are all or none. And they always are maximal in their amplitude. Local potentials are reversible. They return to the resting membrane potential as soon as the stimulus ceases. Action potentials are irreversible. They always go to completion once they've started. Once they're initiated, they're all go. Local potentials has the effect of only works for short distances. Action potentials are self-propagating, meaning they can move a great distance from the point of origin. Local potentials are decremental, meaning the distance grows weaker with time. The signal grows weaker with distance. Non-decremental means that the signal remains the same regardless of how far they move. The maintenance of the resting potential, membrane potential, is possibly due to what? What would you say?
D?
Say it one more time. I'm sorry, you cut in and out.
Yeah, my internet saying it's being unstable. Sorry, can you hear me now?
Yep, what would you say?
I was saying D.
D, why do you say that?
Because of the actions of the sodium and the potassium. I don't know. I'm
You're
just messing.
right. You're right.
Okay.
But what does the sodium potassium pump need to be able to work? It keeps pumping sodium out and potassium in, but what does it also need to work?
Calcium? No.
Nope.
Calcium?
Nope. Why did you say D is in delta?
What? I know.
Because it needs ATP, right?
Yes.
Yes. Okay. So it's always pumping sodium and potassium against their concentration gradients. That's the reason it's both A and B. So we remember that the signal conduction speeds have to do with the diameter of the axon and whether it's myelinated or non-myelinated nerve fibers. So we have both. We have unmyelinated axons and we have myelinated axons. Unmyelinated axons are voltage gated channels along the entire axon length. Myelinated axons are voltage ion channels that are scarce in the myelin-coated internodal regions. So there's about 25 channels per micrometer squared in the internodal regions in between where it's myelinated. Remember, internodes meaning the nodes of Ranvier, meaning the little gaps in between the myelin sheaths. However, at the nodes, there's 2,000 to 12,000 channels per micrometer squared. So voltage gated completely along the axon length or only channels in at the nodes. So how does this signal conduction work? At the with unmyelinated fibers, remember how an action potential is self-propagating. So it's got that positive that positive feedback loop that keeps it self-propagating. When an action potential occurs at a trigger zone, the sodium diffuses a really short distance along the plasma membrane. The resulting depolarization opens more voltage-gated channels immediately distal to the action potential. And the sodium potassium channels open just as they did in the trigger zone, and a new action potential is produced. These first three steps are going to occur continually until the end of the axon is reached. So the result is that we have this non-interrupted wave of excitation along the fiber called the continuous conduction. It's just continuous, it just keeps going all the way down. So it self-propagates itself and it's just continuous all the way down. That's why we call it a continuous signal conduction. So continuous conduction is a repeated nerve signals along the entire length of the axon. The nerve signals are traveling waves of excitation, depolarization, produced by self-propagating potentials. Well, what keeps them moving in one direction? It's the refractory periods. Only the membrane ahead of the potential is going to be sensitive to stimulation. because the refractory pairs keep the signals from moving backwards. So this occurs like a wave-like sequence without losing amplitude. Remember how these action potentials are non-decremental. So they keep going and they don't lose strength as they move down. And they keep going in one direction because of the refractory periods that keep them moving forward because they can't move backwards. In contrast to the unmyelinated nerve fibers that are this continuous conduction, myelinated nerve fibers work in a saltatory conduction. Remember that in myelinated fibers, there's very few ion channels in the internodal regions that are covered by myelin. So no action potentials occur in the areas that are covered by myelin. When the sodium enters the nodes of Ranvier, it diffuses a short distance along the internodal region. So it enters here, and then it diffuses a short distance. Each sodium ion has an electrical field around it. It's a positively charged ion. And individual positively charged ions are going to repel one another, right? Because like charges repel. So the sodium ions are going to repel each other down the internodal regions. They can't move backwards, so they're only going to move forwards. So no sodium moves very far in these regions, but the electrical repulsion between the ions is going to result in an energy transfer along the axon membrane called the axolemma. Saltatory conduction is like a crowded subway car. I have not ridden the subways here in this area, Washington, D.C. area, Baltimore area, when it's really busy. However, I lived in Japan for about 17 months. And while I was there were times when we rode the trains during a really busy time of the day. And the trains are so packed that they have people who push people into trains. That's their job, is to push more people into one subway car. And so picture that, and then picture everyone wanting their own space. Everyone wants their own personal bubble. So the doors open and the sodium rushes in. Well, we all like our own personal space, so we can't be too squished. So more people get on at the next doorway, and nobody's getting out at that moment. So everyone gets pushed to the rear of the car to make more room. No passengers are out ultimately moving. There's just in one specific direction. They're just moving because there's no other way to move. There's no other way to go. So there's a crowding and a transfer of energy from person to person that forces those at the rear to move a little forward, being pushed to the next node. So it just slowly pushes people forward because they can't go backward. Pushes the ions forward because they can't move backwards. Myelin works to insulate and assist conduction in two ways. It seals up nerve fibers. Remember, this is like up to 100 layers of lipid. So ions are not going to be able to move through it very easily. So it prevents leakage of sodium ions in between the nodes. Also, these increased layers of lipid are going to cause the negative charges or the positive charges and negative charges inside and outside of the cell to not be as attracted to one another. Usually when you're attracted to someone, you tend to stay in that location where they're near. Well, what if the further the distance gets away between the ions here, the less likely these ions inside here are going to be attracted to the ions out here, allowing them to move further down. So there's a greater separation between the intracellular fluid and the extracellular fluid. Sodium ions are going to move more freely within the axon, transferring energy easier from one ion to another. So saltatory conduction is going to be very fast if you're not continually having to reinitiate the action potential. It's going to occur a lot faster if you only have to do it every once in a while versus continually. So conduction may be slower at the nodes of Ranvier than it is throughout the rest, but it only happens every like 10 times versus 100 times. Continuous, you're having to reinitiate it every time. Saltatory, you only have to do it at the nodes of Ranvier. So you only have to reinitiate it 5 times versus 500 times. That's the reason saltatory conduction is so much faster. So conduction occurs fast in the internodal regions with excitation at each node creating excitation at the next node. You can think of myelination as being and unmyelination as being continuous, meaning having to dribble a basketball down a court, versus saltatory conduction being able to dribble it once and pass it. So just at first, any questions? Input zone is going to receive incoming signals from other neurons. So this is where we get presynaptic neurons synapsing with postsynaptic neurons. This is where the trigger zone is, which is going to initiate an action potential. Along the conducting zone is where we're going to conduct action potentials along the axon. trigger zone initiated, then it fires the action potential down to the terminal arborization or the axon terminals, which is going to release neurotransmitter that's going to affect other cells. A synapse involves a presynaptic neuron and a postsynaptic neuron or cell. So if you think here, a synapse, and then there's a presynaptic, meaning before the synapse, postsynaptic, meaning after the synapse. And I like to think of a synapse as being a snap on a shirt. You have one layer with another layer. The presynaptic neuron is going to release neurotransmitter, which the postsynaptic neuron responds to. The presynaptic neuron can synapse with the postsynaptic neuron on a dendrite, a soma, or even the axon. One given spinal motor neuron can be covered with about 10,000 presynaptic neurons. So one neuron can have up to 10,000 synapses. One motor neuron. In the cerebellum, one postsynaptic neuron can have up to 100,000 synapses. So this is how one neuron receives information from other neurons and how they pass along information. We have electrical versus chemical synapses. Electrical synapses are where adjacent cells are joined by gap junctions and ions diffuse directly from one cell into the next. What is a gap junction? What's a gap junction?
Is that the space in between the neurons?
You're close. You're very close. I think you're referring to a neuromuscular junction. Thank you. What else could it be?
The synaptic cleft.
You're close. You're kind of thinking the same way Sarah was there. A
Okay.
gap junction is like a tunnel between the two cells. One membrane has half of the tunnel. The other membrane has the other half of the tunnel. They come together and connect, making a full tunnel. And through this tunnel, ions can diffuse directly from one cell into the next cell. These are found in some neurons, neuroglia, and cardiac and smooth muscle. These are key, especially a good example of this is in cardiac muscle, because all of the heart muscle has to contract and relax at one time. This is how that's done, is via gap junctions. So this allows for synchronous activity and quick transmission. Chemical synapses are where neurons are going to communicate via neurotransmitters. So this is where we have sites of memory and the target of many prescription drugs and the site of action for many addictive drugs. Many drugs work on neurotransmitters and their effects. Many addictions occur because of drugs that work on neurotransmitters and their effects. Electrical synapses are where an action potential is going to spread from one neuron to the next via gap junctions. There's no neurotransmitter needed. You see, here's the half of one tunnel, here's the other half. They come together from a full tunnel. They're extremely fast and they allow for two-way conduction. A chemical synapse is where the axon terminal contains synaptic vesicles containing neurotransmitter. And all these little vesicles in the axon terminal that contain neurotransmitter. The synaptic cleft is about a 20 to 40 nanometers, so 10 to the minus 9th gap between presynaptic and postsynaptic neurons. The postsynaptic neuron has neurotransmitter receptors. That are going to respond to the neurotransmitter once it's released from the presynaptic neuron. In all synapses, there is a synaptic delay. So here we have the presynaptic terminal. It's going to release neurotransmitter into the synaptic cleft. The neurotransmitter is going to diffuse across and bind to a receptor. And then a response is going to occur in the postsynaptic cell. This diffusion and binding is gonna take a moment. Nothing occurs instantaneously here. So this is what we call the synaptic delay. So neurotransmitters are substances that are synthesized by a neuron and released when a nerve signal reaches an axon terminal. Most neurotransmitters are released via exocytosis. What that means is that some neurotransmitters are not going to be released via exocytosis. So keep that in mind. There are more than 100 neurotransmitters that have been identified, but most fall into 4 major categories. Acetylcholine is by far the most common and most understood neurotransmitter. However, we also have amino acid neurotransmitters, glycine, glutamate, aspartate. These are all amino acids, these 3 well-known amino acids that also function as neurotransmitters. Gamma aminobutyric acid, or GABA, is a derivative of an amino acid. Monoamines are neurotransmitters that are amino acids that have had the carboxylic acid removed. These include epinephrine. You've heard of people who carry EpiPens. Catecholamine, a neurotransmitter. Norepinephrine, dopamine, serotonin, and histamine if you struggle with allergies. I struggle with allergies really bad year round. Fall season is exceptionally hard for me for some reason. I think it's the mold in the air that just makes my allergies really bad. Histamine is your culprit. When it comes to allergies. The last category is purines. Purines, adenosine, remember that's one of the nitrogenous bases that makes up DNA and RNA. And adenosine triphosphate, that energy currency also works as a neurotransmitter. We also have gases and neuropeptides. Gases are nitric oxide and carbon monoxide. Nitric oxide is why Viagra works. Neuropeptides are what they are, small chains of amino acids. Remember, a peptide is a peptide bond. That's where the word comes from. So one amino acid bound to another amino acid. So a neuropeptide are small chains of amino acids that work in the nervous system. Gases are going to diffuse out of the axon terminal and into the postsynaptic neuron rather than binding to a receptor. Nitric oxide is also a neuromodulator, which we'll talk about later. Neuropeptides are stored in secretory vesicles and can also function as neuromodulators. Guys have any questions for me? Okay, let's stop here. We will move from here into this onto 109 on we'll stop here and we'll start here on Thursday. We will finish, I really want to finish chapter 12 on Thursday. We will start chapter 13. You're going to see that chapter 13 will move a lot faster. Have a wonderful week, 2 days.
You too. See you Thursday.
See you
Thank
Thursday. Frankie or Kevin, are you here?